We are live, I think.
You hit record?
Oh shoot, yeah. Let me do it. Good call out. I think it's recording. Did you guys accept? You got it? Oh,
Oh
Mikey.
shoot. Oops. Sorry. Ah, how do I get back? Okay.
Okay, let me move a few things. That's okay. We can. Okay. All right. Hello, everyone. Welcome to a brand new episode of Corecast. I am your host, Tim.
Now, Mikey.
This is Sahil. Welcome everybody to a brand new exciting episode of Quirkcast. If you haven't already, do join our Discord channel. And if you're watching this on YouTube, do ask us questions during the episode. We do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern. So without further ado, let's get to it. So I guess we've been going on this whole particle journey of talking about different particles from gravitons to inflatons to Higgs and so on and so forth. And then we talked about each of the forces. Last episode, kind of an amalgamation of different forces together and how they're related. So I guess we can start by looking at maybe more of like the matter particles themselves and start with the most like oddball ones out. So I guess Tim, can you lay down like the groundwork of like how particle physics is structured in the sense, just give our audience an idea of like what the basic structure looks like, super high level.
Yeah, I guess I would say a good part of particle physics is it's a little bit like chemistry back in the days, right? We had
Hey, don't say that.
well, I mean, back in the days, we didn't know atoms were made of different constituents, so we kind of studied the various properties of the different, chemicals, right? But now that we've moved on particle physics, we know that we have these set of fundamental particles, and there are quite a few. There are force carriers, matter particles, and of course, the first order task is to lay out what they are, how many of them there are, and then the second task will be, given that we see these particles, what are their properties? What are their fundamental interactions? And some of these fundamental interactions are pretty basic. It's kind of like particle physics version of 1 plus 1 equals 2. And I guess the analogy would be kind of like chemical reaction, right? Although not quite the same. It's like if you have one type of, let's say, quark particle plus some force particle, what did you get? Right, and then you can kind of write these down, and I think that would pretty well categorize the job of a particle physicist, kind of at the basic level. I don't know, Mikey, would you agree?
Yeah, I mean, um, yeah, I guess it's similar to chemistry in the sense that, but it's deeper than that though, right? Because like in particle physics, there's a box, right? And stuff goes in and stuff goes out, and particle physics is about the fundamental rules that determines what kind of stuff can go out in what kind of stuff can go out given whatever goes into it. Um, and one of the things that can happen is particles can actually change their species. So I don't know. I get a little bit confused when people try to enumerate what are all the different kinds of particles. So there's some way in which all the particles can be viewed as kind of like one particle. Or if you really want, you can take one particle and split it up into all its different parts and call it, 8 particles.
Oh, that's an interesting thought. I guess like without us going too deep in the rabbit hole, what do you mean like one thing splitting it apart and getting like 8 different particles? Like
Like
to
for
me, an
example,
electron is different and a proton is different. Like, how can you say
sure.
those are the same thing?
Oh yeah, not electron and proton. Those are about as far apart as two particles can be. But like we often talk about the gluon as though it's just a single particle, but there's
Mhm.
actually 8 different distinct gluons with a different color, what we call color charges, and it's really these 8 different gluons that gives rise to what we call the strong force. And with the photon too, we can say that there's 4 different photons, right? In a sense, or three.
Oh, are you? I think photons strictly two, right? The two polarization.
Oh yeah.
But unless you're referring to the electroweak gauge boson, but but
No,
but
yeah, no.
I think the conundrum is that kind of like the periodic table, right? Like similar elements, we tend to group them together. like the Nobel gases, like they're kind of similar, but we think of them as different elements. But in particle physics, the line's a little murkier, right? They're groups of particles that tend to they're kind of like neighbors, and some of them are so similar, like the gluon, the 8 different type of gluons. But then beyond this superficial difference in their color charge, they're essentially the same thing. So we don't say there are 8 different types of gluons. So there's a little bit of zoology, I would say, involved to group them. But I think overall it's quite clear, right? We have a way of enumerating all the particles that we see, at least in particle
I want
physics.
to call it zoology, though, right? It's like because the rules that determine which particles we view as kind of the same, and which ones we view as different are
Yeah, not
very
not
simple, very powerful.
yeah, not
You know,
yeah.
there's a sense in which, sorry.
Well, I would just say maybe zoology is a strong word. It's not quite as arbitrary. There's a reason behind the madness. Let's let's put it that way.
Yeah.
Hmm.
Like there's a sense in which the up and the down quarks, can be viewed as the same particle in some sense,
Kind
especially as you
of.
turn up the temperature. Especially as you turn up the temperature, they start to kind of melt together. Um,
So, guys, I think we've gone too much in the weeds. Let's take a step back for a moment. For the purposes of this discussion that we're having, what is kind of the categorization of particles what you'd like the audience to know about first to kind of lay the groundwork
I guess
when we
it.
talk about the most troublemaker
Yeah.
particle?
I guess I would like personally. I'd like to view them as kind of like a tree structure, right?
Okay.
So first, I think we can say that there are 2 distinct categories of particles. The ones are the force carriers, the ones that are related to forces, and then there's the matter particles. Those are very distinctive categories. The force carriers, you can have things like particles of light photons, maybe graviton, maybe the W and the Z
Wait,
boson.
can I just admit to that? Because I think I agree with everything you said, but I just wanted to there's 2 types of particles. There's particles that spin at a rate of uh, Planck's constant, and there's particles that spin at a rate of 1/2 of Planck's constant. And the ones that spin at the rate of Planck's constant we call force carriers, and the ones that spin at half the rate we call matter particles.
I see. I guess like so. Okay. Well,
Wait,
well.
can I
I
even?
want to. What's up?
I didn't mean to stop Tim. I just wanted to add that. I think you.
No, no. Okay. All right. Then. Tim, why don't you go ahead?
Yeah, well, not to get into technicalities. So they are different characteristic, and the spin, it's not to go into technical details. It's one of them.
It's not technical. It's just the rate at which they're spinning.
Well,
That determines.
they're not literally spinning. It's almost like a category. I would say.
I
I would.
mean, they're spinning. They have angular momentum. That's what it means to spin.
Okay,
So
well, we can save that for a different discussion. Okay, but anyhow, they are the force carriers. I think undeniably, right? And then they are the matter particles, right? And then the Higgs boson, it's kind of somewhere in an odd ball, and you could think of it as a matter particle, or you could think of it as as the
no,
force carrier.
fudge factor.
You think of it as like a force carrier? I think
No, I said it's a fudge factor.
huh?
It's a fudge factor.
Yeah, I mean we'll discuss which one it belongs to closer. I think it could be somewhat subjective, but there are these 2 categories now, right? And then you can go in further, right? The force carriers, like what types of force carriers? There are quite a few. And then for the matter particles, you can also have similar different types of matter particles, right? Um, I don't know. Should we go in? Should I go into to the different types?
I would say, yeah, like at a high level, so there's the force carriers, the strong, weak, electromagnetic, and gravity that we know so far, and then for matter, what would you say there are
Yeah.
at a high level?
So
Two broad categories.
so a lot of the particles are somewhat unfamiliar to our everyday life experience, but they are. I think roughly you can break them down into particles that are similar to quarks, which are the constituents of protons, and particles that are similar to electrons, kind of the things that orbit around nuclei. So we broadly categorize them as, I think there's names, right? Quarks and leptons, right? That's it. So the quarks, the distinguishing factor is that quarks have strong forces. They tend to kind of clump together in some ways. And the electrons, the lepton family, are more ephemeral. They're kind of aloof. They don't like to hang out with the other particles very much, but they are quite important for our universe.
Gotcha. Okay, so you describe quarks as like hanging around together. They're like buddies with each other due to the strong force, and then you have things like electrons and other particles that tend to be a bit more scattered, a little bit more like sparse. Is that a fair statement?
Yeah, I think that's fair to say, right? Like quarks are, because of the strong forces.
Quarks are gluey.
Yeah.
Quarks are gluey, and leptons don't know anything about glue.
Although we'll clarify that a little bit later. There is one exception, I would say. There's always some exception, but
Exception to what?
huh?
Exception to what?
Well, there's one quark that's a little of an oddball, right?
But it's not like a lepton or anything.
Yeah, it's not, but yeah.
Yeah. So, okay, so we have this one oddball quark. Can you describe kind of like how quarks are structured? Is there one of them, two of them? How many of them are there?
I think technically we can say it's 6, and that's the
Okay.
best answer, right? And if you go to Wikipedia, it's the up quark, the down quark. Those are the ones that make up protons and neutrons. But then there's the weirder guys, right? There's the strange and the charm. Well, actually, I should go in order. So up and down, they're different in that up has a positive charge and down has a negative charge, although the amount differs, right? And then it always comes in these pairs, right? So up and down, and then there's the charm and the strange. The charm is kind of positive, the strange is negative. And then there's the top and the bottom. The top is positive, the bottom is negative, right? So those are the 6 quarks that we have. And we have a similar category for leptons as well.
I couldn't help but notice you stated them in pairs. Why don't you call 6 together? Why is it two per like these, I don't know, 3 broad categories of up down by itself, then charm strange by itself, then top and bottom by itself. No, I mean, like you know what I mean. You said they come in pairs. Why is it pairs?
I think it's important to note that, like, with all of the matter particles, it's one of the great mysteries of particle physics that they always come in sort of like 3 families. So in a sense, there's like really just 2 quarks, the up and the down, but then there's these heavier copies of them, which we call the charm and the strange, and then there's yet another heavier copy of those, which we call the top and the bottom. So these pairs get repeated 3 times, and so that's like the most fundamental observation about why we pair these things.
And Mikey, would you also say this holds true for like leptons, like the whole family of particles that are electron-like and whatnot as well?
Yep, it's exactly the same. Yeah, the electron's heavier cousin is called the muon, and then the even heavier one is called the tau. So it's weird.
Yep.
All the matter particles come in like 3 families, we say.
Yeah. I think
Gotcha.
I think there was a famous quote, like, right? Was it by Gelfand or whatever? Like who ordered that? Like we actually we actually don't have a really good idea why it comes in 3. Like the fact that we have things
No
like
idea what it comes in 3.
like, I mean, our universe is mostly made up. Well, at least the visible universe is mostly made up of protons and neutrons and electrons, right? It only needs the first family, right?
Yeah.
It's like
The universe would look more or less exactly the same without.
sort of. Yeah, although with an asterisk, right? We don't really know the details, but it's like we have a really nice family. This is like almost like the American dream. This is the picket fence, the really the model family, and then there are these oddball neighbors, right? The charm and the strange, and then there's the muon, on the lepton side, and the neutrino, and then there's the top and the bottom. They're even weirder. And then
No, but it's
the
important to
tau.
remember that they're exactly the same. So I don't know if that's a good analogy. Like it's striking. Like if you look at everything except for the mass, or namely the weight,
Yeah,
if you took away the idea of weight, these particles would be literally indistinguishable from each other.
they're
So
almost duplicates, except they're not duplicates. Except one fact, I would say, except the Higgs. The Higgs is kind of like would it be fair to say it's like the cop on the city? Like it's like the sheriff, and it's because of this weird Higgs thing. The mass is all different, and then the properties are drastically different, just because the Higgs.
I see. I see. So I guess like nothing really sticks out to me that like there's like a worse particle or there's like something really odd. It seems very neatly like packed into three things. I also want to clarify one thing before we get to that. Is that like is the reason that they are like within I don't know what you call generations, the same like these two quarks are within each generation is because like they don't go from one they don't transfer from one generation to the next or how do you distinguish between generations my question like what is it that separates generations.
it's literally just the observation that they're copies. I don't know.
I think experimentally you can distinguish it, right? The weak interactions tend to stay in the same family. Like the
Mhm.
same
Well,
particles.
we didn't we didn't
Huh?
even talk about how particles can.
It's not exact, but most of the time, particles in the same family, they kind of hang out with one another. They interact with one another.
Mhm.
Yeah,
But
what Tim's referring to is the fact that the weak force can change the species of a particle, and when it does so, it tends to change it up into a down, charm into a strange,
yeah,
and a top into it. It doesn't tend to cross
yeah,
families.
it's like three different families that they're not very good neighbors to one another. They don't really chit chat that much, right?
Yeah. So I guess I'm gonna throw this on to Mikey. Tim laid out a very nice picture of like how these things fit very nicely. What's the big deal? What's the problem?
Okay, so yeah, I think before we talk about that, yeah, it's just Tim had mentioned the Higgs, but I just wanted to back up a little bit because like there's kind of this, we said that these particles, these generations, they're identical in everything except for their mass, how much they weigh, right? And
Hmm.
we know from previous podcasts that this property we call mass is actually uh, is uh, a byproduct of the fact that there's this thing called the Higgs particle. Um, and the Higgs particle plays a very special role. It literally endows every other particle with the property we call mass. And so the way that works is like this: like we have these like massive particles, right? If we were to turn up the temperature really, really high, like at a temperature that is approximately equal to the mass of the Higgs in energy, um, you would start producing Higgs bosons. And then you would notice that um, these quarks actually don't have different masses. They actually have the same mass, but they have different interactions with the Higgs boson. So the
Hmm.
more you interact with the Higgs boson, the higher your mass is. The less you interact with the Higgs boson, the lower your mass is. Um, that's basically how the Higgs boson gives rise to the property of mass. So if you were actually to increase the temperature, you would see that these particles are actually identical to each other because now they're all massless, but they're interacting with the Higgs. And then when you lower the temperature, their interaction with the Higgs basically freezes out, and then you get these particles with different masses. Um, so okay, that
Wait,
probably
this
clarification.
this was super interesting. I want to stop on this for a little bit. So you said you increase the temperature, like, can you explain kind of what is like what does that mean if you like increase the temperature and like why don't we see like the Higgs in like everyday life or like why don't we observe it very often? Why does it take
So,
energy, higher energy to see it?
yeah, so like that's such a good question because it segues into I think the answer to the question, which is like right. So um, in everyday life,
Hmm.
like just day to day, like if you look at like a patch of empty space, it's actually not empty. You actually have particles and antiparticles coming out of nothing and then canceling each other out. So we like this what we call the quantum vacuum energy.
Mm-hmm.
But those particles only stay alive for like a fraction of a fraction of a fraction of a second before they cancel each other out according to the uncertainty principle. But if you were to increase the temperature up to a point that it's like roughly equal to the mass of these particles, then there's enough energy in empty space to actually make these things real. And so you would have these particles literally just being created out of nowhere. So as you increase the temperature, heavier and heavier particles become commonplace.
I see. Can you briefly explain what does temperature have to do with like math, or like how are they related to each other?
Oh, it's just the energy density. So that mass is equal to energy equals mc
Mm-hmm.
squared.
Mm-hmm.
And so if the energy density in like like a cubic nanometer of space is equal to the mass of a particle in mc squared units, then there is now enough energy there to actually create the particle, and so that particle will be created.
Yeah.
So, real quick, Tim, I just want to make sure I clarify this. So, if you increase the energy density of space to be equivalent to like the amount of energy in an electron, for instance, does that mean electron positron pairs would appear everywhere more?
Yep. Exactly.
Oh,
Yeah.
okay. All right. Okay, Tim, go ahead. I have my question.
Yeah, I guess it's not. I mean, temperature is just a way for us to access the physics at these energy regime. It's not strictly necessary. But what happens when you dial up the energy is that the surrounding, like the Higgs feels like a different surrounding, and as a result, the frozen, we know that in our universe, the Higgs field itself is kind of frozen, and if you increase that energy, the Higgs, it will slowly feel that perturbation, and ultimately, when you increase the temperature high enough at some critical point, super hot, right? I don't even know how many Kelvin or Celsius that is, super duper trillions and trillions of degrees. Then the Higgs will actually kind of melt, and all the masses of the particles will sort of go away, and the only thing that's left is the interaction with the Higgs. So I mean, if we do this thought experiment, you'll see that the interaction with the Higgs boson is what gives rise to mass, and also you can do similar things. You can measure decay of the Higgs, or in collider experiment, you can do something like that. You can create Higgs boson, excite it, and see the interaction. You also see that the interaction itself is pretty much proportional to how much mass a particle has. So this has been confirmed experimentally.
That makes sense. So how does this relate to like the worst particle, or back to the original question? I'm gonna throw this off to Mikey.
Okay, so I would say what's the worst quark? Actually, it's just terrible. Like if you actually look at the masses of the particles of the quarks, they're all like pretty light. But then there's this one quark called the top quark, which is it 100,000 times more massive?
Wait, no. Let's get some numbers straight. So the top quark is 175 times the mass of a proton. It's almost like the mass of a lead nuclei. It's crazy. It's crazy heavy, and it's even heavier than the Higgs boson. Like the Higgs boson is 125 times the mass of a proton. The top quark was just like, what the heck, right? And if you think maybe that's normal, just look at the bottom quark, like the second heaviest. That thing is just 5 times the mass of a proton. It's like 20 times less. And then all the other quarks are way lighter. And the up and down quark are just puny, right? It's like, I don't know, 1,000 times lighter, probably more, 10,000 times. I don't exactly know the numbers. But like, the top quark is weird. Like, given the fact that they all, like, can you just imagine, like, given these are all like the same kind of family, they hang out, they have similar interactions. You just scratch your head and be like, what the heck, right? Like everything else the same, but just this one fact. Somehow it's like a glitch in nature. Just this top quark, 175. Like, what the heck?
Yeah, imagine you saw like a family and they were perfectly normal and perfectly like healthy in every single way, but there was this one one family member that was 1,000 times larger than everyone. It would be odd, right? That's kind of what it looks like. And I don't want to be, what would be the word, like sizist against things that are large, but it's actually causes a lot of problems for physics too, because
Yeah.
what it really means is that the top quark talks to the Higgs so strongly and so much more strongly than
Yeah, it's got a really weird relationship with the Higgs for some reason, and it's completely unwarranted. Like there does not need to be a quark that needs to hang out that much with the Higgs to hit the Higgs field and the Higgs boson. There does not need to be, right? And it comes with real consequences actually. With such a large interaction, it causes problem for the universe. Actually, like literal problems for the
like
universe.
for the stability of the universe. It
Yeah.
makes the universe unstable.
Yeah.
Wait, what does this mean unstable? How can a heavy particle make things unstable? Like,
Oh, it's
I mean, we're
terrible. It's
like
terrible. Yeah.
we're heavy. Like, what's the big
influence
deal?
influence is so, because remember its mass is how strongly it's talking to the Higgs, so it
Yeah.
has a really strong influence on the Higgs, how the Higgs behaves, and there's many scenarios in which this influence that exerts on the Higgs can lead to the Higgs actually being unstable.
Yeah. So I think you
What?
can. Huh? Oh, go ahead.
Oh, I guess. Well, actually, Tim, you go ahead. I was just gonna ask, like, what does Higgs unstable even mean to begin with? Like,
Like it can
what is?
behave
Yeah,
for other things.
Yeah. So we're going back to the Mikey situation, right? The fact that in vacuum particles can pop in and out. This applies to every quark, including the top quark, and this fact, meaning so you can imagine a situation in vacuum, a top quark can pop out, and as they pop out, because it has such a strong influence on the Higgs boson and the Higgs field, it can drag the Higgs field a little bit, right? And what it does is it gives a tendency, the top quark, a tendency to drag the Higgs field to a higher and higher energy value. What that means is that I guess this is an analogy. So people say the Higgs field is sitting on a Mexican hat potential. It's kind of like a ball. It's kind of like a ball in a bowl, right? It's sitting there nice and pretty. It doesn't like to move, right? But just imagine, a force that want to drag this ball up the hill, and because of the top quark, at some point this hill might actually go back down again into like an abyss, like an infinite abyss, a cliff to nothing. That's what the top quark is driving. It creates this extra abyss in which it can drag the Higgs field toward. And when that happens, hell's gonna break loose. The universe will decay. Like there's nothing we can do to stop it. So
Wait, how would it decay if the Higgs shifts? Like, what does that mean? The Higgs interaction changes with things. The mass of things change. Like,
Yeah, that's what
what's
I would be
going
saying.
on?
Yeah, the Higgs gives mass to everything. So if the Higgs
Yeah.
value change, then the
oh
mass of
yeah,
everything
it will be really
such
bad.
all atoms fly apart instantly. Like,
Wait, so does this mean everything will become massless, or like what does this mean?
we're not sure. Like, it depends on what happens with it after it falls. Like, if it if it if it lands somewhere else, which is possible, then all the masses would just suddenly change to a different value, a different hierarchy, and there'd be some whole new kind of chemistry. It would be like if Thanos actually um, decimated the universe.
Wait, I think it's worse. It's not 50%. It's the entire thing.
No, I mean that I'm not going to just kill 50% now. Now I'm going to shred every single atom.
So
Um,
do we have any hope? Like, is there any hope for us?
no, I mean I think it's like this. It's not likely that this. Well, it seems unlikely this will happen just from the fact that we exist. That's anthropic argument for that. But yeah, the top quark. It's true. I'm like I feel like I would bet a lot of money that like without the top quark, physics would not change at all, right? Like with the other quarks, you can argue well, maybe they mediate some process, would cause some small difference and some value. With the top quark, there's no way. There's no way that it
Look,
affects anything
I'm
like
not
chemistry.
I'm not sure. I think I would back to differ a different opinion. Of course, if you given the current physics at face value, you could argue that top quark might be useless.
At low energies. At low energies.
Sure,
I'm
sure,
sure it
sure.
has normal time.
Yeah, but chances are, I think there might be deep secrets hiding in the top quark.
Yeah, that's what makes it intriguing.
Yeah.
Like people, I think the people who are the kind of like the sharpest people who are doing like LHC work were like really focused on that third generation. The top work is so weird. There must be some kind of key in there to understanding what comes next.
And it seems so conspicuous, right? Like there are many theories that says maybe the top quark has something to do with the Higgs field, the Higgs boson in the first place. Like the fact that the Higgs, like probably without the top quark, the weirdest particle would be the Higgs boson, right itself. Well, actually, even with the top quark, the Higgs boson is pretty damn weird.
Yeah,
And the
and
fact
zero.
Right, and the fact that they are so close in terms of interaction, like the top quark really likes to hang out with the Higgs boson. It's a little suspicious, right? Like I feel like they might be conspiring something. Like maybe really in our universe without the top quark, maybe the Higgs field wouldn't even be where it is today, and maybe the Higgs field, the Higgs boson, and top quark might be part of a larger structure that we don't know. I think these are the intriguing questions. But it's a really it's not easy theoretically. It's very tough, right?
No, that's yeah. I was going to say like the other reason why the top part sucks is like it's so hard to write down a theory that gets the top part that heavy. It's so hard. Like
I
if
guess
you're trying to explain like write down a theory that explains where the Higgs comes from, and you have to like do it in such a way that it makes the top quark 172. Like it's so hard. Like it just yeah, it
Yeah,
doesn't
it doesn't want to do
well.
that. It's just like nope. But
I guess on the topic of being having it very hard to write down a theory, are there any theories that speculate on this?
Yeah, there's a ton, but
there's a
like
ton.
most of them stretch themselves really hard to like make it work. It's like you take a nice theory and you just like stretch it to make it sound more heavy, and then publish it.
That's fair. That's fair. Is there significance to the top quark being heavier than the Higgs, like versus if it were lighter than the
Oh,
Higgs?
Yeah,
there is. Oh, there is. It killed supersymmetry. I think that's fair, right? That's kind of
yeah.
fair. But anyway,
No, no, it prefers a light Higgs.
no, but the heavy top, I think really screws it up.
Well, no, it makes it difficult. That's what I mean by stretching.
It's a theory killer for sure, but well, I'm not sure if it's fair to say it kills supersymmetry. Well, that's a topic for different times. It used to be a very popular theoretical model, but it's no longer in fashion anymore. But yeah, I don't think people expected the top quark to be heavier than the Higgs. It's unusual at best.
Yeah.
Gotcha, gotcha. So we are almost at time, and wanted to ask you guys to leave the audience with a few thoughts.
Top work sucks. Well, that
Case closed.
Yeah,
sucks. It's just the worst.
I
The
mean,
worst.
maybe I'll leave it on a more positive note, right? Like maybe on the surface, top quark seems like a weirdo, like really like an outcast, good for nothing particle. But I like to think that nature is smarter than us. Like maybe there is a purpose for top quark. Maybe it's not such an awkward particle and such a weird thing after all. And I surely hope that there is some beautiful symmetry somewhere hidden in our universe that we just have not uncovered it yet. That will really show that the top quark maybe perhaps really is a benevolent particle, like without which really the universe would be a whole lot different. But until then, we really don't quite know what to think of the top quark. It's certainly not the top. Well, it's top in a different way, but certainly not the top quark in a positive way, I guess.
There are definitely, for sure, secrets inside the top quark, and we're gonna catch it and gut it and then put its head on a spike.
Seems like you have a vendetta against the top quark, Mikey.
Yeah, it's yeah.
The bane of your existence.
It's got some coming in.
Yeah. So actually, before we head out, Tim, one of the audience members asked, which app are we using to generate the transcript? They mentioned it's very impressive, so wanted to give you a chance to answer that.
Oh, it is just Zoom. So.
Okay. All right. Well,
and I
there you go.
apologize for the volume situation. We will try to normalize it better next time. So thanks for the feedback.
Yes, very much appreciate the feedback on that. So, all right. On that note, I want to thank everybody for joining us, and we'll see you all next week.
All right. See you.
Yeah.
Bye.
Bye.